Fighter jets cross 20,000 meters without strain. Helicopters, heavier and more powerful per kilo, collapse near 7,000. Same sky, same air, completely different ceiling. And the reason isn't the engines, it's geometry hidden in physics. A commercial airliner cruises near 12,000 meters while passengers calmly sip coffee above weather and storms. A fighter jet climbs to 20,000 meters and still has powerful thrust to spare above clouds. Yet a helicopter, the most versatile flying machine ever built, begins to suffocate at roughly 7,000. It shakes, it stalls, it refuses to climb. An invisible wall in the sky only rotorcraft can feel. This wall is not folklore. It is written into rescue manuals, into military doctrine, into engineering equations. Pilots call it the ceiling, designers call it the limit. Physics simply calls it absolutely inevitable everywhere. The real reason is hidden in the air itself, in molecules thinning as altitude steadily increases upward. More than 60,000 civilian and military helicopters operate across our planet at this very moment globally. They evacuate the wounded from battlefields. They lift stranded climbers from icy ridges of remote mountain ranges. They deliver organs between hospitals and crews onto oil rigs, often the only machine able to arrive. And yet, look at the map of Earth's tallest mountains and notice something strange about the summits. Everest stands at 8,848 meters. K2 rises to 8,600. Kangchenjunga, Lhotse and Makalu, every single one pierces a layer of sky where helicopters simply cannot operate. The summits remain almost entirely beyond rotor reach, suspended in air too thin for spinning blades alone. Engineers separate two altitude numbers.
The service ceiling is where helicopters barely climb, about 100 feet per minute. The absolute ceiling is where climbing stops. For most helicopters, both numbers sit between 5 and 7,000 meters. Above that line, the air thins, the rotors fail, the engines starve. The consequences are not theoretical. Climbers have died on ridges visible from valleys below because no rescue aircraft could reach them in time. Soldiers have been stranded on high passes. Avalanche victims have waited for help that physics simply refused to deliver. But here's the thing. One mountain has already broken this rule. Once. The year is 1955. The Cold War shapes every branch of engineering. France is determined to dominate rotorcraft and own the vertical skies. Test pilot Jean Boulet steps into a slender experimental machine, the Sud-Ouest Jean, later the Aerospatiale Lama. His mission is simple to describe and nearly impossible to execute. Climb higher than any rotorcraft has ever climbed. Boulet rises through 5,000 meters, then 6, then 7, then 8. The rotor disc thins its grip. The engine gasps. The controls grow soft and unfamiliar in his hands. And yet, he keeps climbing. At 12,440 meters, nearly 3 kilometers higher than Everest, his turbine flames out. The combustion chamber, starved of dense oxygen, simply quits. There is no power, no thrust, no second chance.
What Boulet did next became legend. With both engines dead and air too thin to fly, he entered autorotation. Rotor blades driven by the rising airstream kept spinning like a samara seed falling from a tree. He glided down through 12 kilometers, descent controlled by nothing but the geometry of unpowered spinning blades. He landed safely on the ground. His record still stands. No piloted helicopter has ever flown higher, not in 70 years, not for any prize, any nation, any reason. And that silence tells you something. It tells you that 12,000 meters was not a milestone. It was a warning carved in altitude. But here's the thing, his record exposed a deeper flaw. Boulet did not prove helicopters could fly high. He proved they could only survive that height by falling out of it. To understand why, examine air itself. Air is not empty, it is a fluid, a sea of molecules pressing against everything that moves through it. At sea level, every cubic meter of this sea contains about 1.25 kilograms of mass. That mass is what wings push against. That mass is what rotors throw downward to lift a machine. Climb higher and the sea thins. Air density drops by roughly half every 5.5 kilometers. At 6,000 meters, the air holds only half the molecules of sea level. At 12, just a quarter. The same rotor swinging through the same arc grabs less and less of the world with every meter climbed. A helicopter rotor is not a propeller, it is a rotating wing slicing endlessly through the surrounding air. Each blade deflects air downward, and that downward thrust of air pushes the entire machine upward into flight. The amount of lift it generates follows a brutal equation. Lift equals air density times the blade's velocity squared, all multiplied by the wing's surface and shape, and as you climb higher, that density term silently collapses. Density appears once in that equation, but velocity appears squared, so when density falls, lift falls in lockstep. To recover the loss, you must spin the rotor faster. And here the problem becomes purely geometric. A helicopter blade has a root near the hub moving slowly, and a tip far away moving very fast. On a modern medium helicopter, the tip already travels at 220 meters per second. That is nearly 2/3 the speed of sound, almost no room left before the sonic wall. And yet, density is only half of the problem. The naive answer to thin air is obvious. Just spin the rotor faster, push the blades harder, squeeze more lift out of less atmosphere. Every engineer who has faced this problem has tried that path. Every one of them hits the same invisible barrier. A helicopter, unlike an airplane, flies forward by tilting its rotor disc slightly into the direction of motion. At any given instant, half of the rotor rushes forward through the air, while the other half sweeps backward. The advancing blade adds its rotational speed to the helicopter's forward speed. The retreating blade subtracts it. If a tip moves at 220 and the helicopter flies at 80, one side touches 300. The other side drops to 140. A single disc torn between two completely different worlds. This phenomenon is called dissymmetry of lift, and at extreme altitude it becomes absolutely catastrophic for any rotorcraft. The retreating blade, slower through the air and starved of density, cannot generate enough lift to sustain flight. It stalls, airflow detaches, the blade stops working, and one entire side of the helicopter loses support. Pilots feel a violent shake, a sudden roll, a nose pitch they cannot correct from the cockpit. Meanwhile, the advancing blade faces the opposite disaster. Its outer tip approaches the speed of sound itself. Shock waves form across its surface, drag explodes, and brutal vibration tears at the rotor head with destructive force. The blade is no longer flying, it is being pummeled by relentless transonic compression on every pass. Spin faster, the advancing blade fails. Spin slower, the retreating blade fails. There is no escape window. Climb higher and the gap between them widens until both catastrophic failures happen simultaneously on the same rotor. The real reason is asymmetry, not weakness. The rotor never runs out of strength, only of margin. But here's the thing. What they don't tell you is that the engine also fights this altitude. Most modern helicopters are powered by turboshaft engines, close relatives of the jets that propel commercial airliners worldwide. Yet they are adapted to spin a shaft instead of producing thrust. Extraordinary, precise, supremely engineered machines. And yet, by pure physics, they remain altitude sensitive in a way no engineer on Earth can fully escape. A turboshaft draws in air, compresses it, mixes fuel, ignites the charge, and harnesses expanding gas to spin turbines. Every step depends on density. Thin air means less oxygen, less combustion, and dramatically less shaft power available. At sea level, a turboshaft produces 1500 kilowatts. At 6000 meters, the same engine yields 40%. No mechanical change occurred. The compressor turns the same speed. The fuel is identical. Air simply refuses to feed it. Pilots in mountainous regions know a phrase by heart. Hot and high. Warm air is even less dense. Warm molecules spread apart. On a summer afternoon in the Himalayas, a helicopter faces two penalties at once. Altitude robs half its power, heat robs it again. Some operations on high passes become impossible after noon. While the engine loses power, fuel burn rises. The pilot demands more torque, more thrust, more energy per second. Range collapses, payload collapses. A machine rated for 2 tons at sea level may lift only 400 kilograms. At 6,000 meters, sometimes it carries only its own pilot. The Everest rescue corridor has a hard limit. Helicopters can reach base camp at 5,364 meters. They sometimes nudge toward Camp 2. Above that altitude, they become almost useless. Even if they could physically reach it, they could carry nothing meaningful. Not a body, not a wounded climber, not even spare fuel for descent. The mountain simply outranks them entirely. Against all odds, one helicopter touched Everest summit. May 14, 2005, a mission that rewrote history. French test pilot Didier Delsalle climbed into a stripped-down Eurocopter AS-350B-3 Squirrel that morning, a single-engine light utility helicopter modified for one mission. Extra weight removed, seats taken out, sensors fitted precisely, fuel reduced to the absolute minimum needed for descent, engine tuned to extract every last watt from thin air. Delsalle launched from base camp, climbed for 50 minutes, and approached the summit of the highest mountain on Earth. Wind conditions were almost still, temperatures cold enough to add density to the air, every parameter by chance aligned. He touched the summit at 8,848 meters, holding contact for 2 full minutes. Skids pressed into the highest patch of ground on Earth, rotors spinning in air no rescue machine ever touched. When he lifted, descended through the death zone, returned. An extraordinary achievement, almost certainly the last of its kind. His flight was not really flight. It was controlled compromise, stripped airframe, perfect day, atmospheric gift, pilot's edge. Notice what it took. No passengers, no payload, no fuel margin, no wind, no heat. Remove one, impossible. Take 2 advantages away, and the helicopter cannot leave base camp. The operational ceiling has never moved. Manuals print the same number. Insurance companies draw the same line. Military planners assume the same envelope. 7,000 meters, a boundary so consistent it has become a kind of constant in rotorcraft engineering. The secret lies in what engineers refuse to build. Because here is the strange truth about that ceiling. The 7,000-meter limit is not only physical, it is also economic. A higher helicopter is technically conceivable. Engineers have sketched it many times. It would require much longer blades made of far more exotic composites. An engine oversized for sea level just to retain useful power at altitude. Pressurization, oxygen systems for crew, redesigned transmissions, custom fuel controllers. Every system reimagined for an environment helicopters were never meant to enter. It could be built, but the math is brutal. To gain 15% more ceiling, you double the cost. You halve its payload at low altitude, triple its maintenance burden. No customer would ever buy such a machine. No rescue service could afford it. No army justifies it. Above 6,000 meters, each 100 costs more. More in design, fuel, weight, and risk.
Engineers call this the diminishing returns zone, where physics and economics agree. That is why no manufacturer crosses the line. Not because the technology is impossible, but because the value disappears. The ceiling at 7,000 meters is not built by nature alone. It is a wall agreed by engineering. A number where physicist, accountant, and pilot all nod and quietly say, "This is where we stop climbing."
But the next generation may rewrite this rule entirely. For most of aviation history, rotorcraft have been trapped in one architecture. One main rotor on top, one tail rotor on the side, one engine, one ceiling. That architecture is starting to break apart. A new class of machine is emerging, abandoning the single rotor altogether. Distributed lift designs spread the work across many small electric rotors, sometimes 8, sometimes 12, sometimes far more. Each rotor is smaller, lighter, and can be tuned individually. Some prototypes climb far past where conventional helicopters surrender. Because no single blade must bear the full asymmetry of altitude, a constraint older rotorcraft could never escape. Then come compound helicopters. The Sikorsky Raider X adds a forward propeller, sharing the lifting burden with the rotor. The rotor no longer does everything. The aircraft flies faster, higher, and longer than any traditional helicopter ever has. Even Mars offers a lesson. NASA's Ingenuity helicopter flew where atmosphere is barely 1% as dense as Earth's. Its blades were enormous compared to its tiny body, spinning at nearly 2,400 revolutions per minute. It proved rotorcraft flight is possible in conditions far worse than Earth's highest summit. The lesson is a blueprint. Engineers now study hybrid tilt rotors and electric vertical lift machines, targeting operational altitudes of 9,000 meters and beyond. New battery chemistries, carbon composites, and active rotor controls together may finally lift the ceiling for special demanding missions. The ceiling is moving. What seemed permanent law, helicopters below small aircraft, is now being quietly renegotiated. Not abandoned, negotiated. The 7,000 ceiling remains, but shares the sky with machines that ignore thin air entirely. When you next see a helicopter cross a valley, watch carefully. Just hovering, it is doing something extraordinary. It fights density, asymmetry, transonic shockwaves, retreating blade stall, fuel curves, and engine losses all at once. It does this so smoothly, we forget the simplest hover is itself a quiet negotiation with raw physics. We forget that above the ridge, above the clouds, lies a layer of sky belonging to wings, not rotors. A region the helicopter, for all its versatility, must look up at, like climbers facing summits they cannot reach. 7,000 meters, a number written nowhere in nature, yet printed in every flight manual ever made. The quiet verdict of engineering, an honest answer to a question that sounds simple, yet remains aviation's deepest. If these engineering boundaries fascinated you, this channel holds more films on the invisible limits shaping modern technology. If you wonder how electric flight, new alloys, and Mars-tested rotors might redraw the sky, the next film awaits. Subscribe to continue the exploration. The next frontier already waits.